This is the virtual machine. And here is the notebook. If you want to run a cell, is it large enough? Maybe I can make it like this. So if you want to run a cell, you do cell, run cells, run all, and then you have no problems. It will just run all the cells and create the figures that you are interested in. The names of the figures you find in the manual. That is also a click on the website, so you can read it yourself. If you, let's say, just again want to plot this, if you want to execute a cell, you place your cursor in a cell and you do Control Enter. But if you do it now, you get an error message. And why? Because this one ends, and you were running all the cell with clean. So if you ran with clean, everything is gone and you have to run all the cells again. So cell, run all cells, then it works, run all. If you don't do clean, then you can just, doing step by step all those things. Here you see the output characteristic of a FET. Here I have a GM sweep, so a current and a GM. And you see here nicely. Oh, let's maybe also do this and relate it to the previous lecture. Let's make it a little bit smaller. I have a FET here, 40 microns wide, 500 nano long, and I'm plotting it with a VGS around 0.9 volt, plotting the GM as a function of VGS, so the current is plotted. And I'm changing VDS. So let's just look at the upper lines that you have the highest VDS. And you see it's, let's say, the square root characteristic, which means we are working with the transistor in strong inversion. If I reduce VDS to, let's say, something like 0.5 volt, then I'm just a little bit going above threshold of this device, then probably it will run in weak inversion. In weak inversion, I have an exponential characteristic and the GM is proportional to the current. Now let's see how this works. And this is how you can study this device behavior. So I do run all because just lazy. And this is the output characteristic. And here we get. And you see now GM is proportional with the current. Current is very low, and we are definitely working here in weak inversion. If you make VGS very high, let's make it 1.5 volt, then I go to much higher current levels. Probably I will encounter vertical field mobility reduction and maybe also in velocity saturation. So let's see what runs, what is this, what this will give. That's the output. And here we will have, and now you see, here we have maybe the square root relation, but here it starts to saturate. And if you go even further, if I would go to 1.7 or 1.8, well, you can do 1.8 also, but then we enter also the linear region, of course. You have to be careful for that. Otherwise you're mixing up. So if I do 1.8 volt, you really see the saturation of the GM that we have talked about. This is because of vertical field mobility reduction. And this FET is not, it's, if I make it 180 nanometers, then it's even more horrible, of course. Let's make it a 180 nanometer FET, because then it is a short one. And run it again. And now, look, we don't have only saturation, but it even becomes less. And that can be because of the vertical field mobility reduction, that it really is the DM drops again. Of course, we are also entering the linear region, so don't mix up the things too much, but you really see this square root function for GM isn't valid at all for short channel FETs in strong inversion. Here you really see this happening. You see that going to the at point 2, point 3, what is it, at 30 milliamps, this fat, this, what is, no, this is 20 milliamps. So this is 5 milliamps at 2 milliamp or so. You see it happening. So this tool is a very helpful tool to help you understand the operation of a FET. And this library that is connected, the CMOS18 library, is a free library available for educational purposes. It is not really mapped onto a process, and it is let's say you should have in many more details and resistors in it and pads in it, whatever, to make a complete IC. But this is really very helpful for learning. And maybe you can also see the breakdown and the drain induced barrier lowering. If I increase here the VDS to 2.5 volt, because all this has all effects modeled. And here you see it happening. Breakdown and drain induced barrier lowering probably together. The process is made for 1.8 volt, but here at 1.8 you see already that the current is increasing. So with this tool you can design a FET such you can make many more plots. I have here a lot of plots, and there is a example notebook in this new version. Is an example notebook with many different plots. So please study it, change the parameters, and try to understand how the design of the MOSFET affects its behavior.